Hello everyone, so we continue with undetermined coefficients method, and I have already explained what happens in the non-resonant case, and now we have to discuss the resonant case. So in the non-resonant case there was a result that if lambda related to the form of the components of B was not an eigenvalue of the linear part, the homogeneous part, then this was the form of the particular solution, and the degrees of these polynomials q1 and q2 were at most equal to degree of p. Now, what happens when this condition is not satisfied? What happens when lambda is an eigenvalue of A? Then this result fails. There will be no xp in this form, but we can fix this by changing the form of xp. So let's discuss the resonant case. If the components of Bt are expressions with some polynomials and exponentials and cosines and sines, and this number a plus or minus ib is an eigenvalue of A, it could be even repeated. We assume that it has multiplicity k. Then the form of the particular solution is this, so it looks similar to what we had before, but that time the degree of q is larger. So if lambda is non-repeated as an eigenvalue of A, then it doesn't have any multiplicity, which means it has multiplicity 1, and then you just add 1 to the degree of p. This is similar to what we had for higher order equations. You had to multiply things by t, well, it was x for higher order equations. You had to multiply by x or x squared and so on because of the resonance, and now we have to increase the degrees of these polynomials. Let me show you several examples of resonant and non-resonant equations. So let's take this example. A is 0, 1 minus 1, 0, and B is cosine t minus sine t. Now, this value of lambda related to B is plus and minus I, and it is the eigenvalue of A. I is the eigenvalue of A, it is not repeated, so k is 1. Now, if you replace this b by something else, let's say sine of 2t, then this the number lambda related to b becomes 2i, and it is not an eigenvalue of this matrix. So this case is non-resonant, and xp should have both components sine and cosines of 2t, and this case is resonant, and x should involve t multiplied by sine, t multiplied by cosine, and sine and cosine as well. Now let's have one more example. Now A is 0, 1, 1, 0. It has eigenvalues 1 and minus 1, and B is e to the power t 0. This number lambda is 1 over here, so it is the eigenvalue of A, which means that this is a resonant case. 1 is non-repeated, so k is still 1. Now if I replace B by anything else, like say sine, then the number lambda related to this B becomes plus or minus I from this formula. Plus or minus I is not an eigenvalue of this matrix, so this is a non-resonant case. And the third example is when the multiplicity is higher. This matrix 1, 1, 0, 1 has repeated eigenvalue 1. So if I add this b, then it is not just resonant. The degree of resonance is 2, because this 1 is a repeated eigenvalue of A. So this is the resonant case with k equal 2, and when you try to find xp, it will have to involve not just e to the power t, but also t e to the power t and t squared e to the power t. But if I replace b by something that only involves e to the power 3t, then this is a non-resonant case because 3 is not an eigenvalue of this matrix. Let's have an example of a resonant equation. I chose same matrix A as before, but different b. b used to be e to the power t, and now it is e to the power 2t, which is a resonance. So first of all, I'm writing out the complementary function, same as before, same as in the previous example. And now I notice that this 2 also appears here in the complementary function, which means that I have resonance. This 2 coincides with this 2. So xp will not just involve e to the power 2t, it will also involve t e to the power 2t. This is the form in which I should find xp. I have 4 coefficients here. For undetermined coefficients, I will have to find them all. Now I'm substituting xp into the equation, which is not really pleasant. So what I do is x1 is this expression, I differentiate it, and this is my x1 prime. Here it is. It has 3 summations because I have to differentiate bt e to the power 2t. That's what I get. And then this is my x1, this is my x2, and this is e to the power 2t. So this is my first equation. I just substituted my xp. And I do the same with the second equation. Now, to figure out what happens, I will show you in red all terms that involve t e to the power 2t. All the rest of the terms just involve e to the power 2t. And here you have t. The terms in red have t in them. So if you want to have equality, you should have that the red terms equal all the red terms and black terms equal black terms. So you should equate coefficients at t to the power 2t and equate coefficients at e to the power 2t, which gives you 4 equations. So this first equation says that the red terms add together in a proper way, so 2b equals b plus d. And then the second one is about black terms in the first equation, and so on. You have 4 equations on 4 coefficients a, b, c, and d. Now there is a little problem over here, because you may notice that these 2 equations are dependent. This is often the case in the resonant case. You have more than one solution. This system is degenerate and you will have more than one solution. This is not a big problem because what you need is just one xp. You don't need to find all xp, you just choose any. So what I did, I just set c to 0 and then there is only one solution. But you could also set a to 0 and get a different solution. It will still work. And then this is your final solution. X is a complementary function from here plus particular solution from here, but now you know the values of a, b, c, and d, and you can substitute it here. This is your solution of the initial equation. Now I wanted to stress that the undetermined coefficients method is a shortcut in comparison with variation of parameters, because when we variate parameters, we will have to compute the fundamental matrix for this a, then invert it, then integrate. And here you didn't integrate anything. What you did is just you were solving the linear system. So in many cases, even in the resonant case, this is a great shortcut, and if you can, you should use the undetermined coefficients method. Now comes the last remark. Suppose that the right-hand side of your equation, the non-homogeneous part of your equation, is a sum of 2 different expressions of different nature. How can you handle this case? That's how you can handle it. Suppose that you can solve the equation x prime equals ax plus b1. Suppose that you can also solve x prime equals ax plus b2. So you know their particular solutions, xp1 and xp2. Then, if you just add these particular solutions, then the result solves the equation with b1 plus b2. So when you add particular solutions, you will also add non-homogeneous parts. The proof is you just notice that xp1 is a solution of this equation, and write down that xp2 is a solution of the second equation, and then you add both expressions and get that the sum of xp1 and xp2 solves the equation with b1 plus b2. So, for example, today we had two examples of non-homogeneous equations with one and the same linear part. One was non-resonant with e to the power t in B, and the second one was resonant with e to the power 2t. Suppose that we have this equation. When your non-homogeneous part has both e to the power t and e to the power 2t, then the method of undetermined coefficients doesn't apply directly, because you need to have one and the same lambda in all exponentials here. But that's how you can handle this. You can split your b into two summands and solve separately. First you solve this equation with this b, and then you solve the second equation with the second b. We have already solved both equations. These were our example number 1 and example number 2, so I already know particular solutions. I just copied them from the previous slides, and this is my answer. I add the complementary function, the solution of the homogeneous part, and the solution of the equation with this b. This is a non-resonant case, so you only have e to the power t here. And then I add the solution of the equation with this as a non-homogeneous part. And this is a resonant case, so you have this t to the power 2t in your expression. And the whole sum is the solution of the non-homogeneous equation. That's how you can handle the case when your b involves exponentials of different types. You can just split your b into several summands and solve separately.